Okay, here is my third hands-on project. It's a simple feed-forward neural network with the MNIST dataset. I chose TensorFlow because I wanted to use their functional API. It's just my comfortability. And then, so here I'm going to load the dataset from TensorFlow's Keras module, and we can see the shape here's 60,000 hand-drawn images, and they're pixels that are 28 by 28. And then for our next step, we need to handle the grayscale. So we normalize, since the grayscale is 0 to 255, we have to take each pixel and get it between 0 and 1, because we don't need to know the exact color of gray, we just need to know how gray it is. And this will it'll put a lot less of a tweak on data as we go forward. And then I need to convert these sets into tensors. So then xtrain. So our data still looks the same from here because we haven't done anything to the 2D yet. But each of these images 2D, and we need it to be 1D because TensorFlow wants like a 1D vector. And so we'll take every pixel and just put it into line. And you can see here that makes 784 because that's the amount we get from 28 by 28. And so now that we have a 1D vector, we'll one-hot encode the labels, so that way we'll have our 10 possible predictions, 0 through 9. And then here's the shape of that data. And then here we'll move on to model architecture. I'm going to have 4 layers. I have an input layer, 784 nodes, because that's 1 for each pixel. So that way we evaluate the entire image. We're using activation function ReLU, and ReLU rewrites each response so that when a neuron activates, it's either active or silent. Because and the way this happens is we remove all the negative numbers and just mark them 0, because we don't need data to swing negative. We just need to know that something is very active. And so this just works better for the math side of things and for like efficiency. And then I have 2 dense layers, and then we have our final layer, which will only be 10 neurons, because we're doing 0 through 9, we only have 10 possible predictions. And we use softmax. Softmax activation is going to convert the result into a prediction, so a number between 0 and 1, probably a float, because we don't need, it's just statistically better. That's the way statistical prediction works. And then right here I will define the model, and then we'll train it. I'll just roll back to the summary so you can see the 4 layers and how many neurons and the parameters. And then now we'll compile. We're using the atom optimizer. We're doing categorical cross entropy for loss. And then I'm going to go ahead and fit it. I chose 5 epochs. It's worked great for me so far. And then we'll just go ahead and run those. I'm trying so hard to keep this under 7 minutes because I really tend to ramble, and I can't imagine watching 30 videos for 13 classes. Okay, so we have, we've gotten to a 92% accuracy. This is actually the lowest I've gotten, I think. And our loss is not, it seems like it keeps going down. So if I were still working on this, I'd probably add another epoch. I think I'm just going to back this up again, because usually I get in 97, 98%. And that doesn't matter for the success. Or, you know, how well is the training? It's odd. This isn't as good as I was getting before. Well, it's in my README. Okay, so now we'll evaluate it. So our test accuracy was only 91% this time, and our loss 0.29. But let's do an individual prediction. So I've set it up. I'm using the matplotlib, and we're gonna like rebuild one image so we can look at it with NumPy. So here's our true label number 2, and then we will see what our prediction. And we got it good this time. So we got our number 2. We were able to predict accurately. Read this number 2. I'm irritated because I was getting 98% accuracy, and of course this moment I'm not. But I guess sometimes the numbers are not on your side. Well, yeah, that's all I've got. This was really fun. It feels neat to be doing this sort of analysis. So, yep, that's it.